So in the last class, I think he started this section, average and the standard deviation. I think we went halfway through, but because to new students, we'll start from the beginning. I'll go from the start here. Okay, this is something happening here. News connection. So, in the previous section, we learned about the histogram. So, what we can do using a histogram? Why do we need a histogram sometimes? Right? When do we use histograms? For what kind of data do you use a histogram?
Present large amounts of data.
Large amount of what type of data?
Quantitative data.
Yeah, that is the important thing. Right? Histogram is used for quantitative data. Mainly for, we have two types of continuous data, quantitative data. What are those two types?
Continuous and discrete.
Continuous and discrete. Yeah. The histogram is mainly used for continuous data. Right? So, what is the main purpose or purposes of a histogram? When do you draw a histogram? For what purpose?
Data is distributed.
Yeah.
A lot of.
Because when you have a large data set, there may be some numbers repeating, the same number repeating, or maybe in a given interval, a certain number of observations, in another interval, maybe a less number of observations, and so on. So we want to sometimes see how the data are distributed within different intervals. Right? So that's what we call the distribution of the data. Distribution of the data. Right? Data are distributed within some range. In different sub-intervals, the number of observations are different. Right? So if you want to have some idea about how these data are distributed, usually we use the graph called histogram. Right. What are the main features of a histogram? Histogram, for many people, it's looked like a bar chart, right? But there is a big difference between bar chart and histogram. What are the main differences? When do you use a bar chart?
To present discrete data.
Yeah, you can use bar chart for discrete data also, but mainly we use this bar chart for qualitative data. Qualitative, right? Nominal or ordinal data. Right? You can use it for discrete case also. But in bar charts, almost always the height of the bars represent frequency or relative frequency or percentage. Height is equal to one of those three things. Right? If you want to compare two bar charts, usually we use relative frequency or percentage, because frequencies will not work, because in the two samples maybe the number of observations, the total number of observations may be different. So in that kind of situations, frequencies cannot be compared. Another one important thing in bar chart is usually the bars are separated. There are always gaps between bars. Right? We don't draw them together, touching each other. Right? Yeah, we leave always some distance between the bars. Right? As far as the histogram is concerned, no gaps between bars. We should not leave any gap between bars in a histogram. That is, as I mentioned, we use this mainly for continuous data. So in order to show the continuity, we don't leave any gap. If we leave a gap, somebody gets an idea that this may be discrete. Right? So in order to show the continuity, we have to draw this thing without leaving any gaps between bars. Another very important thing in histogram, different from the bar chart. Sorry? Yeah, that's right. That's the most important thing actually. That is, in a bar chart, usually the frequency or the relative frequency or the percentage is equal to the height. But in a histogram, height is not the important one. Area of the vase should be proportional or equal to the relative frequency or the percentage. Right? So that's the most important thing. Right? So what is the purpose? As we mentioned, usually we draw this thing to get some idea about the shape of the distribution of the data. Why do we need to know the shape? Why shape is important? Shape is important because when you go to analyze data, we have to use different types of techniques. Right? So people have produced large number of techniques for different purposes, but always when people produce those things, there are some assumptions always, underlying assumptions. This method is suitable for this kind of data for this purpose. Right? So there are some purposes and assumptions. So most of the techniques that we use, for example, make the assumption that the data are symmetric, for example. This distribution is symmetric. Right? A particular type of symmetricity is called the normal distribution. Right? So most of the standard techniques have been developed assuming that the data distribution is symmetric or normal. Right? So in order to see whether we can use those methods, first of all we have to make sure that our data distribution is symmetric, for example. Only then when we know that our distribution is symmetric, we can use that method. Right? So otherwise, for example, if we see our distribution is not symmetric, then we have to choose an appropriate method for that kind of data. For example, you may have something called skewed, positively skewed or negatively skewed data. Right? So you cannot use some method that is developed for symmetric data to analyze skewed data. Theoretically, you can just put the numbers into the computer and ask it to apply that method, but then the results will not be valid. Right? So therefore, having some idea about the shape of the distribution before starting any analysis, any advanced analysis is very, very important. Right? So that is why we usually draw the histogram, especially when you have numerical and continuous data. So what you have is here is not the histogram, actually some smooth version of histograms. In order to actually get some idea about the shape of the distribution using a histogram, you have to have a reasonably large data set. Right? It may not be enough to have 20 or 30 observations. Right? You have to have a reasonably large data set to get a correct idea about the shape of the distribution. So that is one disadvantage actually, but there's nothing we can do. If you want to get a good idea about the shape of the distribution, you need a fair amount of data. Right. So the shapes, as far as the shapes are concerned, there can be different shapes, but mainly when you look at the smooth histogram, these are actually ideal ones, but practically the smooth ones will not be exactly like this. But roughly, what we are doing is actually using some kind of models. Right? So as far as the models are concerned, you might sometimes, for your histogram, you might be able to use a model like this. So that is what you usually call the normal distribution, bell-shaped symmetric distribution. So you draw the histogram and see whether you can approximate your histogram using a curve like this. If that is possible, then you can assume that your data have a symmetric distribution, and therefore you may be able to use some method developed assuming that the data are normal. Right? Or you might have a histogram which might be approximated by this kind of curve or this kind of curve. Right? We call them skewed. Right? So this one we say is positively skewed. Right? This is called the tail of the distribution. So here this one has a tail to the right side. So it's called right skewed or positive side, positively skewed. For this distribution, this is the tail here. So that is, tail is going to the left. So it's called left skewed or negatively skewed. This direction is the negative side. direction, this is the positive direction. So those are the very smooth situations, but in practical situations, of course, you may, all these situations you have something called one mode, only one peak, right? One peak. But in practice, can be situations where more than your histogram look like having several peaks. Right? For example, it can be probably your histogram may be able to, we may be able to approximate it using a curve like this, right? Which has two peaks, right? We call them bimodal. Right? So that is where usually we start when you have some continuous data. Right? If you want to analyze the data, usually we have to have some idea about the shape of the distribution, and depending on that you choose a suitable technique, right? So you have to have ideas about what are the available techniques for your particular purpose, and then what are the assumptions underlying those methods, and then depending on what assumptions they have, these methods need, and then what kind of data you have to choose a suitable method, right? So once you have a histogram, it gives you a lot of idea about the distribution, right? Which values are more likely, right, in the data, which values have a high frequency, which range, for example, if here, this range, right? There are more data in this range than in this range, right? So it gives you that idea directly. Right? If you look at this kind of ones, right? You can see that this is possible to have large numbers. Right? Most values are somewhat small. Right? They have high frequency, but there's a possibility to have very large numbers also, but with a very small percentage. Like that. So that kind of information is available directly when you look at the histogram. But in addition to the histogram, sometimes people might ask, right? Like for example, if you want to describe a person, you can describe a person using few features, like how tall that person is, how fat that person is, and so on. Right? Few features. Using once you give some ideas about those features, somebody may be able to draw the person, draw a sketch. Right? So like that, in addition to the actual histogram, one might talk about few numbers, numerical summaries. This is a graphical summary. Right? In addition to the graphical summary, you can also give some numerical summaries about your data. Right? So as far as numerical summaries, we should be able to then, somebody should be able to draw this kind of picture sometimes. Even if you don't have the whole data set, if you have some numerical summaries only, using that you should be able to get some idea about the distribution. Right? So what are those numerical summaries which are useful? What are the features that we can talk about in a distribution of data? What are the features? So people usually talk about something called the center of the distribution, center. And the spread, that is another feature. In addition to those, some people talk about something called skewness, how skewed the data, right? What is the direction of the skewness? And there's another thing called kurtosis. Those are the four features that people usually use to describe the distribution of the data, the shape of the distribution. As far as symmetric distributions are considered, actually only two of them are usually enough. Right? So if you think that your distribution is symmetric for some reason, maybe some previous knowledge, or for some reason you think that it should be symmetric. For example, suppose for example you are in a manufacturing facility, say they are filling some drink to bottles. So this has been set up so that 400 liters is filled for each bottle. That is the target. But we know that in practice, not every bottle is going to get exactly 400 liters. Some bottles will have a little bit less than that, some bottles will have a little bit more than that. So if you look at the actual amount in a soft drink bottle, it is not a fixed number, it is actually a variable. So if you look at the distribution, it will be roughly like this. Because there is a target, most of the values will be close to that target, but there is a chance that few numbers, few bottles will be too much less than that, or few bottles only will be too much more than that. Right? So therefore we can imagine that the distribution will be something like that. So in that kind of situations, it is enough actually to talk about the center. Where is the center of the distribution? Where is it located? If you think this is like a building, where is it located, right? We can, when we describe some place, for example, we say, okay, we have to go to a certain building. It is located in this, on this street, at this place. So that is the location. Right? So location or the center is one thing that we can talk about to identify that. And another thing is the spread, right? You can have this kind of shape, or you can have this kind of shape, or you can have this kind of shape, right? With the same symmetry. Right? So therefore, you have, in addition to the location or the center, you have to tell how long the distance, how wide the distribution is. Right? So those two things will give you some idea about the shape of the distribution, especially if it is symmetric. So if it is not symmetric, then that means it is skewed somehow. Not always. For example, here for these kind of distributions we don't talk about that kind of things, but usually for symmetric or only one, that means if it has only one peaked distributions, then we usually talk about skewed. So if it is not symmetric, it has to be skewed. So when you talk about skewness, first of all you have to say to which side does it have the skewness. Is it skewed to the positive side or to the negative side? To the right or to the left? So that has to be indicated by our number. If you are going to use a number, that direction has to be indicated by the number. Right? So usually people calculate something called the skewness, and that number can be positive or negative. The number will be positive if the distribution is positively distributed, right? Positively skewed. The number will be negative if we calculate the skewness for this kind of distribution. So number will tell you the direction, positive or negative, and the sign of the number. The number, size of the number will tell you how much skewed it is. Right? So for example, you can have this with this skewness, or like this, right? Like this. Skewness can be different. So therefore the number will tell you how much skewness you have. How much skewness you have. Actually in this chapter they don't talk about the skewness and kurtosis, I just mentioned it. The kurtosis is another thing that tells you about again the length of the tail, and also the peak, about the peak. Right? You can have a distribution like this, or you can have a distribution like this, right? Or you can have a distribution like this, and so on. So whether you have a very acute peak or moderate peak or something like that, you have to describe that also about the distribution. So here in this chapter we talk about only the first two characteristics, that is the center and the spread. Center and the spread. So actually even for the center people use sometimes three measures depending on the situation. Sometimes people use the arithmetic mean as the measure of the center. Sometimes people use the median as of a center, as for the center, or sometimes people use the mode. But mainly in this book they talk about only two things, that is the mean and the median. Actually they are mainly talking about the mean here. So for the mean, the book is using the word average. So that's what they mean by average. But in general statistic world, when we say average, it may mean the median or the mode also. Right? So specifically if you want to say, you have to say arithmetic mean. Right? Because there are several types of means also. Arithmetic mean, weighted mean, geometric mean, harmonic mean, different types of means are available. So usually when you talk about the center for general type of data, what we mean by mean is arithmetic mean. So that's what I have explained here. This book uses the word average to mean arithmetic mean, but sometimes average, the word average is used in general for the center, not only for the arithmetic mean. Right. So when the histogram is symmetric or symmetric and unimodal, of course, two characteristics like center and the spread is enough to explain that. Otherwise, usually we need more characteristics to explain it. Right. So here are three examples that I mentioned in the last class also. Generally, when people talk about average, it may mean three different things, right? I have given you three examples where the word average is used, but that average word means three different things. For example, if somebody says the average test score of 30 students is 75, average test score is 75. So in that case, in almost all the situations, when you talk about average of some marks, that mean the arithmetic mean, right? Adding all the marks of the students and dividing by the number of students. So that they are used word average. Right? If you look at this example, the average monthly household income in a village of 200 households is equal to 125,000. So in this case, you have to think a little bit. They say average. So what average are they talking about? Usually when you talk about something like income, monthly income, household income, what will happen if you use the arithmetic mean as the center or the average? Yeah, because when you take a sample of people and households and ask them, it's possible in a usual village or town, there are large number of people with some small income, right? Small to medium income. But very few people with very high income, right? Very high income, astronomically large, right? So if one or two people, those people come into our sample, what happens to our mean? Our mean will be huge because of those one or two values, very huge values. Right? We are adding some medium or small values, large number of those values, but then 1 or 2, 10 million, 100 million, that kind of values, and then the mean, arithmetic mean will be very large. And if you say, okay, in this town average monthly income is like 15 million, right? That's giving you a completely wrong idea about the actual picture. So therefore, usually people don't use the arithmetic mean to talk about the average or the center in that kind of situation, because it distorts the real picture. Right? That kind of when do you have that kind of situation? When you have that kind of situation like income, usually the distribution will be like this, skewed to the right. Most of the people will have this less or medium income, but there will be few families or people with very high incomes. Right? So the distribution will be actually positively skewed in that case. So when the distribution is positively skewed, or similarly, if you have a situation like this, then the arithmetic mean is not really a good measure of the average. So in that kind of situations, people use the median as the average. So most probably then in this situation, they are talking about the median. So probably you already know median is the point where we divide the whole population into two equal parts, where 50% of the people will have income less than this number, 50% of the people will have income more than that number. So that is the number by which we divide the population into two equal parts. Two equal parts means 50% will be less than that number, the other 50% will be larger than that number. So probably this average means the median in this case. And the third one, it says the average shoe size sold in a store might be reported as size 9. Right? So definitely this is not the arithmetic mean. They have not added all the sizes they have sold and then divided by the number of shoes sold. Definitely it's not the arithmetic mean. And it may not definitely, most probably it is not the median also, right? You may not say that 50% of the shoes they are selling are less than size 9 and the other ones are more than 9. If that is the case, then it will be the median, but this is not the median definitely. So what is it? Maybe they are just talking about what is the highest frequency, right? What size are you selling most number of times, right? So maybe 9 is the size. So in that case, this average, the word average actually doesn't mean the arithmetic mean. It doesn't mean the median. It may mean most probably the mode of the distribution with the value with the highest frequency, right? So you can see, even though this book here uses the word average for the arithmetic mean, generally average can mean any of these things, right? So this may be a little bit boring to you because you already know these things, how to calculate and so on, but let me just for the completion, let me go through those things also. So if you have a list of numbers, you know how to find out the arithmetic mean, and according to the book, that is the average. So in order to find out the average, you just add the numbers, right? Take the sum of all the x values and divide by the number of values. If you have x1, x2, x3 up to xn, then x1 plus x2 plus x3 plus up to xn divided by n gives you the average, or precisely the arithmetic mean. Right? Usually if you denote your observations by x1, x2 up to xn, usually we denote this average by x bar. That is the usual notation. If you denote your observations by y1, y2, y3 up to yn, for example, in that case you use y bar as the average. So x bar is equal to x1 plus x2 plus up to xn divided by n. So this is what we write down as I from 1 to n xi divided by n. Right? Here n is equal to the total number of observations in the list. Right. So if you have a frequency distribution instead of the actual data, instead of the list of numbers, if you have a frequency distribution like this, ungrouped, simple frequency table, what does it mean? Right? In a frequency table, probably you don't have this column, you will have only these two columns. Right? So it will tell you what are the values appearing in your data set. Maybe x1 is one possible value, x2 is another possible value, like that. These are the unique different values. And then x1 is occurring n1 times. There are n1 x1s, that's what it means. And then n2 x2s and so on. So if you are given this part, then how do you find out the mean? Well, it's very clear. Of course, you have to add all the numbers and divide by the number of numbers. So in order to get the sum of n1 x1s, you have to multiply n1 times x1, and then n2 times x2, n3 times x3, and so on. Add all those numbers, right? So in this case, x bar will be equal to x1 n1 plus x2 n2, and so on. Here I have used the number of possible values to be k. Right? Earlier I used n for the total number of observations. So here x up to xk nk divided by n1 plus n2 plus up to nk. So that's what you mean by x sum of I from 1 to n xi ni divided by n. So this n is equal to the sum of n's, n1 up to nk. Right. So that's why this is this one. But you can, if you want, you can write down the same thing in terms of the relative frequencies also. Right. So in the last class I explained what the relative frequency is. Relative frequency is the same as the proportion. So for this observation, relative frequency is equal to N1 divided by the total one. So that is the proportion of X1s in the sample. And relative frequency here, R2 is equal to N2 divided by N. So we will use them by R1, denote them by R1, R2, R3 and so on. So in that case, I can, now this one is equal to this because this thing is equal to N here. And I can write down this one like this. I can put this N1 times N, N2 times N, N3 times N like this. So this is my relative frequency. Ni divided by Ni, N is Ri. So therefore you can write down it like this. So the average X bar can be written like this or like this. Right. This is in terms of N's and this is in terms of R's. Right. And actually we can show that it is not only that, it can be written as a weighted average. Right. Here also we have a weighted average. Right. These are the weights. N1, N2, N3 up to Nk are the weights. X1 up to Xk are the values. So each X value is weighted by N1, N2, N3 and so on. So when you talk about a weighted average, this is how you usually define a weighted average. Right. Sum of weights times value divided by the total weight. That's how you define a weighted average, weighted mean. Right? So this also can be written as a weighted mean, where Ri's are the weights and Xi's are the values, and I can put it like this because this thing is equal to 1. Right? Always the sum of the relative frequencies is equal to 1. So therefore I can, without any loss of generality, I can write out sum of Ri here. So that shows you that this is actually a weighted average. So you can write down, you can find out the mean in terms of N's and X's like this, or if you want, you can write down the same thing in terms of the relative frequencies. So here is a very simple example. Here the frequencies are given. I have directly used the frequencies to calculate the average. So this is your X bar. So there are 9 zeros in the data set, 7 ones, 5 twos and so on. So we have to just add all those values and then divide by total number. Here is 25, sample size is 25. So 0 times 9 plus 1 times 7 and 2 times 5 will give you the sum of all the values and then divide by the number of values. So that's the mean. There is a usual rule of thumb when you report the mean. Right. If your data does not have any decimal places, for example, if your data are full numbers, usually we report the mean with a 1 decimal place, go one more decimal place. If your data have 1 decimal place, then it's customary to report the mean with 2 decimal places. Right? These numbers will be large, will have more than 2 decimal places sometimes, so you round it in that case to 2 decimal places. So that's not a rule, but that's the rule of thumb, okay? But general practice. But there's a reason for that also. But at the moment I cannot explain the reason for that. So just remember, as a general rule, usually when you report the mean, you report the mean with more decimal point than the data has. Right. So now let us look at, these are not actually in the book like this, but I added because I know that you all are mathematics students, right? You are also mathematics, right? Yeah. Right. So, so therefore, I can talk a little bit about more mathematically, because this book is written for non-mathematics students. I think it doesn't talk about any mathematics. So suppose you have a group frequency table like this, right? You are given the class boundaries, right? Like this, and then suppose you are given only this column and this column, right? Usually you will have only those two columns in the frequency table, right? But then once you are given these class boundaries, you can find out the midpoints, right, in each class interval. Right? So for example, A plus B divided by 2 will be M1, B plus C divided by 2 will be M2, and so on. You can find out the width, right? Notice here the boundaries have common left and right limits, right? So these are called class boundaries, right? Sometimes in a frequency table you might have class limits where there are gaps. In that case, usually you have to remove the gap first of all and get the class boundaries. Right? Okay, so when you find in the width, you have to remember that you use the class boundaries, not the limits. Right? When you find the width of a class interval, you have to use class boundaries now, because here if you are finding the width, you can, because these are boundaries, you can say W1 will be B minus A, W2 will be C minus B, and so on. So you can find. So generally there may be this may have different widths. You don't have to have the same widths. Class intervals may be having different widths. That's possible. And this column and this column will be given usually to you. And once you have that, of course, when you're drawing a histogram, you need the density, right? Relative frequency density or percentage density. Right? If you want to have the percentage density, you have to have another column here giving the percentages, and then you have to convert that into percentage density. That is percentage per unit length. Right? For example, if you have marks here, then you have to calculate the percentage per unit mark. So that's what you mean by the density. So you can do it for relative frequency or percentage. So supposing that you have calculated the relative frequency density, that's coming from relative frequency divided by the width, right? So here the relative frequency will be N1 divided by N, so that is the relative frequency. You have to divide that by the width to get the density. Right? You have to divide that by the width, so then you will get this one. So this is the density, relative frequency density, and similarly relative frequency density here, and so on. So in a histogram, you will be drawing that relative frequency density on this axis, and then class intervals will be shown here, and then you will be your heights will be equal to these values, so that the area will be equal to the relative frequencies. So how do you find out the mean here? X bar. In your A levels, what you do is this. You have to make an assumption, right? Suppose you don't have the original data set, maybe the original data set is huge. So you have a frequency table like this. So you make an assumption here. You are given that there are N1 observations in this interval and N2 observations in this interval. So probably you don't know the individual values now. You only know that there are N1 values in this interval. So you have to make an assumption that you have to represent all those values in that interval by one number. That's the only thing we can do, right? We cannot do more than that. So we are going to assume that all those numbers in one values are equal to M1, the middle value, right? And we are going to assume that these N2 values are equal to this value. So if you assume that, then you can easily find out the average. Of course, this average will not be the exact average of this data set, corresponding data set. It will be only an approximate value in this case. So you will be multiplying N1 times M1 to get the sum of values approximately in that interval, and N2 times M2 to get the sum of those values in that interval, and so on. So that is the usual formula that we use. Right? Ni My summation divided by the total number of observations. But if you want, you can write down it in other methods also, using other, for example, your relative frequency or using the areas of the histogram, you can write down like this. So they are the same as this because is n here. So after that, when you get ni divided by n, you get this formula here. And you can see that ni divided by n, this is for example d1, n1 over n w is equal to d1. So n1 divided by n is equal to d1 times w. So therefore this thing can be represented by, in this case, d1 times w1 for example. So this is diwy. This part can be represented by this. So, and then we know that diwy is also equal to the area. I have denoted the area by ai. So this is equal to this. So you can write down, use any of these formulas depending on what you have and what you can calculate. And then once you come to this place, I can show that that is again weighted average. This is a weighted average at the beginning, but it is, there the weights are ni values, the values are mi values. Here, the values are mi values, the weights are ai values. Right? And we know that sum of ai, where this ai is actually the area, actually area is equal to the relative frequency in this case. Each area in the box is equal to the relative frequency in that interval. So therefore sum of ai will be equal to 1. Right? Because sum of the relative frequency is equal to 1. Therefore I can write down here as 1, and that 1 is equal to this. So these are just few, just playing with numbers just to show that you can write down the same thing in other words as well. None of these are in the book actually. Right. So suppose you are not given the data, but you are given some kind, you have some kind of histogram given like this, and suppose you want to find out the mean x bar. If you are given this percentage density here, so the total area will be equal to then 100. So if you are given this one, how do you find out the mean? Right. What you have here is the percentage density. You know the width, right? So therefore, using those things, we have to calculate the average. So we can use this formula instead of the first formula. We can use this one because we know the densities, in this case percentage densities, we know widths, and we know the middle value of the intervals. So therefore we can use this formula. So from the histogram we can get the mid values like this. From the histogram itself we can get the widths. They have different widths, but we can get those widths from the histogram. And we can calculate these di's because we are given the values here, right? These are the di values, they are given here. So all those are available, therefore it's easy to use this formula here. So once you use, so for each you can calculate di, wi, mi, and we can add them up. So that will give you the mean. Okay, so that's how you calculate the mean, right? Average according to the book's usage. So we use this one at the center or the location of the distribution, center. Why do we call it a center? How does the mean or the average according to the book's usage becomes a center? Actually, we can show that it is a center in terms of, or with the meaning that it is the balancing point of the distribution. If you put this histogram on something called fulcrum, right, with this kind of thing, and if you change it place to place until you get balance, at that point will be the mean actually. We can show that it is balanced, right? The moment, right? That's what Guru Gurutha Kendra, it was a Gurne. So Gurne will be 0 around that. Right? What you call the Gurne is the moment. So moment will be 0 around that point. Right? So let's show that. Let me show it using a simple graph here. Suppose you have a histogram like this. Now in these histograms, we are going to show two things to you. You can see that this part is the common part in those three. We are changing this value here. Right? So suppose you have a histogram like this. Right? This is actually giving you the percentage density. Here the because this width is 1 actually. All the intervals have the same width here, but it doesn't have to be like that. Even with if you have a histogram with different widths, the same idea will be correct. If you have this kind of one, assume that this is some weightless board. Right? Suppose you have this kind of, like suppose this doesn't have any weight, then you can see that if you put your fulcrum or something balancing point there, this will be balanced. Right? But what is that value? For example, here this one is 1, this is 3, so this is actually 2. Right? So if you consider now what are the values that we have? We have 1 here. 2 2s, that's why you have height there. This is the data set. So if you calculate the mean of these 4 numbers, what is the mean? 1 plus 3, 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 divided by 4 is 2. Actually the mean is 2 and the balancing point is also 2. Right. If you now move this to the right side, now what happens to what has to happen? Right? The balancing point has to go to that direction in order to balance generally. So, but exactly where should we put it? Right. Let's calculate the mean first of all. Now, suppose you have here 1, still these two, 1 and 2 are the same, but this number, now 3 becomes a 5 here. So, you have 1, 5. So, the mean will be 1, 3, and then 5 plus 10, 5 is 10, then 2.5. 10 divided by 4, 2.5, and actually this will be the balancing point. In a graph it will be like this. Right? How do you show that it is the balancing point? Take the moment around this point. Right? So if you take the moment, it will be 5 times. Sorry, this the height will be 1. So for example, suppose this is something like wooden blocks or something. Right? So this will have, for example, 1 kilogram. This part will have 2 kilograms. This will have 1 kilogram. Right? So the width is the same. So 1 times this distance to the right, and then this weight times 0. This times then we'll have to ask. We know that the weight is coming from the middle, no? Right? So the weight will be 2 will be like this, and then 1 will be like this, and then 1 will be like this. So take the moment and find out whether it's 0. Right? So it will be 1 times 1 to 2.5, and then minus, it will be like this, and 2 times 0.5, right? And then 1 times 1.5. That will be cancelling out to get 0. So therefore you can see the moment around that point is actually 0, and the mean is also the same point. And similarly, for this picture also you can show that. Actually I have done the calculation here. Instead of 1, 2, I have, you can use if you want, your percentages also you can use. In this case they are using the percentage. So මෙතන 50 එක කියලා ගන්න පුළුවන් වුණා 25 කියලා ගන්නත් පුළුවන්. මෙතන 2 කියලා ගන්නත් පුළුවන් 50 කියලා ගන්නත් පුළුවන් එකම ගානේ ඉන්නේ වැඩි වෙන්නේ. So it doesn't make any difference. So still the moment will be 0. So therefore from that picture it is clear that the arithmetic mean is actually the center point, at least for that picture. Right? So let's look at another one. Right? This is a situation where you have a discrete type of data, not continuous. Right? So in that case your distribution will be like this, right? Kind of a bar chart, not exactly a histogram. Right. So if you have these numbers we calculated earlier, the mean for the same thing, I think it was 1.2 or something, the mean, right? Yeah, mean was 1.2. So if you calculate the moment of this picture around 1.2, you can again show that the moment is 0. You calculate the picture, the moment, right? Assuming the weight is equal to this height and weight is equal to this height, here the weight is equal to that height and so on. So I have calculated that the moment around 1.2 is going to be 9, this height is 9 here, 9 times 1 minus 1.2, here this is, okay, 0, 1.2 here. So 9 times 1 minus, yeah, 9 times 0 minus 1.2, right? So that is the distance, right? Up to 1.2, 0 minus 1.2, 9 times, and then 7 times 1 minus 1.2, right? So like that, to calculate, you see that the moment around 1.2 is equal to 0. So that again shows you that is the balancing point. And I have done that for a continuous case also, right? Assuming, considering this picture here, this picture I have calculated the mean, we have already calculated it to be 50.5 point something here. Here I have written down more decimal places because otherwise the moment is not going to be equal to 0 because of the rounding off errors. Even if I use this number, still the moment around this point is not exactly 0 because this is not ending here. There are more decimal places actually when you do the calculations. There are some rounding off errors. So, but if you find out the moment, you can show that the moment is very close to 0, not exactly 0. It is different from 0 because of the rounding off errors. So you can check these things when you get the note. So theoretically, actually, we can prove that the mean, arithmetic mean, is actually the balancing point of a data set, or in the sense that it is the balancing point of your distribution, right? Histogram or the frequency distribution, right? So in that sense, it is a balance. It is a center because it's a balancing point, right? Now, in this example, they are actually not. Now we know how to calculate the mean and what the mean means. Now here they have shown you an example with some application of mean, and they want to introduce. They wanted to introduce some words also. So let's look at this example. After this example, we'll take a small break. So a survey has been done at irregular intervals. This is something called Health and Nutrition Survey from 1959. At irregular intervals, they have done this particular survey. This HANES means Health and Nutrition Examination Survey. This is the second one. So HENES second example was taken during the period 76 to 80, not in 1 year but several. Again, after that, it was done. Actually, this is the fourth one, third one. They are not talking about that. The survey was done again in 2003 and 2004. This is not actually fourth one. This is the fifth one. Right. So for this particular they are considering the second one and the fifth one. Right. So what they are showing in the book is some feature like that, and they are making some descriptions and talking about this. They are discussing about what you can see. So here, what they are showing on this one is the average heights. Here in this graph, they are showing the average weights. So they have two sets of graphs here for men and women. Here also men and women. So for example, if you consider 1 point, so this dotted line represents the first survey, and this one represents the second survey, 2003 to 2004. Right? So if you consider, for example, 1 point on one line, what does it mean? For example, and this axis actually shows the years, the age of the people. Right? So in the survey that they took for the second survey, for example, they had large number of people whose age was 20. Right? So their heights definitely are different heights, even though age is the same, height is not the same. So there are a large number of people with age 20, and the mean weight of those people was approximately 70 inches. Right. So, and similarly in the previous one also it was very close, but little less, few decimals of inches less than that. Right. So like that, then they considered again 40-year people. Right. Remember, this is even though it looks like okay, we'll talk about that later. This was something called cross-sectional study. Right. They have just looked at the population, taken a sample at that particular time, and then at that particular time in the sample there were 20-year-old people, there were 40-year people, there were 60-year people. The people were not the same; they were different people. So out of those 20-year people, they found out that average height for men and women separately, and for the other people with age 40, again they found out the mean, and 30 also they found out, like that. So they got this graph. So this is kind of a very strong reduction of data. So this 1 point here, for example, represents maybe 1,000 people. Right? There may be 1,000 people in that particular year, and with age 20. Right? Their all heights are represented by just 1 point. Right? So there may have been some distribution like that. So, but we are not worrying, we are discussing about the spread here, just looking at the center of that distribution. So what can you say about the heights of these people, men and women? Let's forget about this weight first of all. So remember these people here that represent, this one is not the same as these people. These people were of age 20 in this year. These people were age 20 in this year. So they are different people. So what can you say?
So height differs from the year that they were born.
Sorry?
Height differs from the year that they were born. So
Yeah, that's right. These people were born, for example, for this point here, these people were born 20 years before this. These people were born 20 years before this. So they are completely different people. But when of course when people are 20 years old, they have come to the highest level of height. They usually don't go more than that, right? So, but here there is something like a drop of height. Here also something like drop, but here the drop here is large, drop here is small. If I say, for example, like this, or somebody else say something like this, people's height get reduced when they get older, right? By this amount, right? It was like here, and then it is very much like about 2 inches shorter than that. Will that be a correct explanation? It will be a correct explanation if what?
we consider generations.
Yeah, that kind of explanation can be used if they were the same people, for example. Right? If somebody was following the same people, right, at age 20 and age 80, and then somehow they observed like this, then they could have mentioned something like this. But here it's not like this. So one thing that the book wants you to understand is actually something called cross-sectional study. The other type is called longitudinal. Right? If you are following the same people and studying what is happening, like for example height or weight or whatever, that kind of study is called longitudinal study. But here we have a cross-sectional study. Therefore, that kind of explanation is not meaningful one here. So, but anyway, what can we say? For example, this is one cohort, one group of people representing this one, and the other one is also representing another group. So there's a slight increase here, but for age, for example, 70 people, there is an increase somehow from this to this. Increase is higher here, and the increase is smaller here. Why is that? These are not the same people, but roughly you can say they are the people with the same age at some point, with the same age, right? Age 70. Right? Why age 70 people have this much differences in height there, and why age 20 people have only a small difference here? For example, if you consider age 70 people here, these people were born 70 years before this, roughly middle of that. Right? These people were born 70 years before this. Right? What is 70 years before this? This is like 2003, and then if you subtract 70, you get 1930 or something, right? 33. Right. So that is again a very old age, right? Long time ago, right? So we are comparing here what was the height of people, the difference between those two people 30 years ago, and what is the difference between these two? 76 to again about 30, right? Roughly 30. 76. Yeah.
27.
Yeah. So these people were anyway born long time ago, and this difference was roughly between 30 years. These people were born very recently, and again there is a 30-year gap, but only very recently born. So taking that into consideration, you might be able to explain why the gap here is larger than the gap here.
So when they were 70, those are two different generations, and again when they were 20, there are another two different
Yeah, yeah. So but why the gap will be that much difference?
food or something.
Yeah, not or something. Actually, that might be one reason, because the health condition and everything were different, completely different at that time, right? Food, nutrition, everything might be different. Of course, there's a very slight decrease. For example, even if you consider these people, if you consider the same people for when measure their heights when they are 80, there might be a little decrease. Because you know always there's some kind of this kind of reduction of height, right? But not this much, right? So this difference might have that kind of change also, because anyone who is 20 is much taller, but the same person becomes, when he becomes 70, right? There might be a slight reduction, right? So that reduction might be there also, even though these are not the same people. These people probably were taller when they were 20, little taller. So there is some reduction, but this complete reduction cannot be attributed to that. Probably this can be attributed more to some other factors, right? Like nutrition and health condition and everything, and maybe some other reasons which we don't know. Right? Okay, so similarly now. The height of a definitely know that usually the average height of men is larger than the average height of women, so that is clearly explained here. Right. If you look at the weight, what has happened? The difference, and what has happened now here there is some kind of reduction, right? Early age people were shorter, now new generation are higher, right? So again here early and new, because they are looking at the age. What has happened to the weight?
Got fat.
Yeah, got fat. When they usually that's what's happened, you know. When people get younger, they become fat, and of course Later on, when they become very old, then of course something goes away and then becomes little thinner, right? So that's explained in the picture, right? So what the book wants to explain was actually one thing is that these kind of cross-sectional data, and therefore you should not be you should be careful when you are interpreting, remembering that these are not the same people, and therefore if you explain it like height becomes decreasing or reduces when the age is reduces this much, or when they get old is not the complete not the correct explanation. So here I have written down some explanation given in the book. Average heights increase slightly in each group. Right? මෙතනදී අපිට පේනවනේ slightly කොහොමද වැඩිලා කියලා. මේකෙත් වැඩිලා මෙතනත් වැඩිලා මෙතනත් වැඩිලා මෙතනත් වැඩිලා. So this is very increased. Right? The increment is larger for the younger people. Sorry, larger for the old people, and increment is smaller for the younger people. Then මේ කාලේ අවුරුදු කියලා වෙනසක් වුණා දැන් ලොකු මේ improvement එක ගන්න the same, right? The kind of food and everything has been almost the same. Therefore, if there is any effect of that kind of thing, it doesn't change that much. In the first one, 1976 to 80 data, the average height of men appears to decrease after age 20, dropping about 2 inches after 50 years. A similar pattern is seen for women. Can we conclude that the average person lost height? No, we cannot. That's what I explained earlier, because this is a cross-sectional study, not the longitudinal. In the longitudinal one, we would have been following the same people, but here it's not like that. Therefore, we cannot come to a conclusion like that. Right? In a longitudinal study, the same people are followed over time and compared with themselves at different ages. In both first sample Hans 2 and Hans 5, observed association between age, average age, and average height and age is mixture of aging effect and the secular effect. Right? So the two other words that they want to explain is here is the aging effect. Aging effect is what I explained earlier. Usually there is a small decrease of height when the people get the same person. So that difference is also included in that large reduction. But more than that, actually, what you have is something called the secular trend. Secular means long term. Long term trend, changing the mean. Right? So that's what is explained by this gap here. Right? So this gap actually contains, this gap has occurred because of two reasons. One is the aging effect, right? And plus something called the secular effect. Here, mainly the secular effect. Okay. So what they have written down at the end as a conclusion, or what to take about from this example is, if a study draws conclusion about effects of age, right? We are considering this as a function of age. Find out whether the data are cross-sectional or longitudinal before you make any conclusions. So I have added few things to explain what the secular trend means, and then what the longitudinal, and I have added few more explanations so you can read them. Right. So I think that's a good place to take a break before we talk about the median. Okay? Take a break about 10 minutes. Then start this section.